Have you ever wondered what makes a car lurch forward? Or, what keeps a planet from just flying off into space? Well, it turns out there's this one single beautiful law that pretty much runs the whole show. And today, we're going to pull back the curtain on it. Okay, just look at this. On the left, you've got a guy just sitting there, totally calm in a rocket sled. Then bam, look at the picture on the right. His face is literally being pulled and distorted by some incredible forces. We've all felt a little taste of this, right? That feeling when you're in a car and someone hits the gas and you feel like you're being pinned to your seat. So what is that? What's really going on? Is there some kind of invisible force that's actually shoving him backward? The answer? Well, it's probably not what you think. And it's going to completely change how you see things moving around you. All right, so let's just get right to it and bust this myth. That pushed back feeling? It's not a force pushing you back at all. The real story is that it's your own body resisting a change. It's a property that everything has, and it's called inertia. So let's reframe this. You're not being pushed back. The seat is actually pushing forward on you, trying to get you to speed up. Your body's inertia is what's putting up a fight. It basically wants to stay right where it was, but the sled, or the car, is forcing it to come along for the ride. That resistance is what you feel. So the main idea here is that inertia is just an object's tendency to keep doing whatever it's already doing. If it's sitting still, it wants to stay still. If it's already moving, it wants to keep moving, just like that. This laziness analogy is kind of perfect. Matter just resists being told to do something different. And the person who put all of this together, the connection between forces, that inertia we just talked about, and motion, was, you guessed it, Isaac Newton. His second law of motion is really the master equation we're diving into today. And this brings us to the science of kinetics. It sounds complicated, but it's really just the study of how forces cause changes in motion. And pretty much this entire field can be boiled down to one super famous formula. There it is, F equals ml. I know, it looks so simple, right? But don't let that fool you. This is one of the most powerful and important equations in all of physics. It tells us that any unbalanced force on an object is equal to its mass times the acceleration it experiences. So let's quickly break that down. F is the total or unbalanced force. It's the result of all the pushes and pulls acting on something. M is its mass, which, as we said, is just the measure of its inertia or its laziness. And A is acceleration, which is just the change in its speed or its direction. Now, this is super important because it brings up something that confuses a lot of people, the difference between mass and weight. I promise you they are not the same thing, and figuring out the difference is absolutely key. This table breaks it down nicely. Mass is the amount of stuff an object is made of. It's inertia. And that amount never changes, no matter where you are in the universe. Weight, on the other hand, is the force of gravity pulling on that stuff. That's why your mass would be exactly the same on the moon, but you'd weigh a whole lot less because the moon's gravity is so much weaker. So on Earth, an object's weight is just its mass, m, multiplied by the acceleration from gravity, which we call g. And if you look closely, you can see it's just a special version of F equals ma. The force is weight, and the acceleration is g. Simple as that. Okay, so that's all the theory, but how do people actually use this law to figure things out in the real world? Let's walk through how it's done. Well, engineers have a step-by-step process. First, you set up a coordinate system, your X and Y axes, to keep track of directions. Second, and this is so important, you draw what's called a free body diagram to map out every single force acting on the object. Third, you plug all those forces into F equals ma. And finally, once you know the acceleration, you can use other equations to figure out exactly where the object is going and how fast it'll get there. So let's try it with a classic textbook problem. We've got a 50-kilogram crate. It's being pulled by a rope with 400 newtons of force. The big question is, how fast is it going to accelerate? And this is where that free body diagram is a lifesaver. We have to account for everything. There's the rope pulling it forward. There's the crate's own weight pulling it down. There's the ground pushing back up. And, of course, there's friction trying to drag it backward. The final acceleration is going to be the outcome of this whole tug of war. So once you do all the math and plug everything into F equals ma, you get your answer. The net result of all those forces is that the crate accelerates forward at 5.185 meters per second squared. It's just a perfect example of how this one little equation can take a really complex situation and give you a clear, predictable answer. Now, so far, everything we've talked about has been in a nice, straight line. But what happens when things start moving along a curve? Think about a car on a winding road, or even a planet going around the sun. Here's a cool little mind bender for you. When a car is turning, it's accelerating, even if the speedometer stays at exactly 60 miles per hour. How is that possible? Well, remember, velocity isn't just speed, it's speed and direction. So if you change your direction, you are, by definition, accelerating. And if you're accelerating, you need a force. And that force has a name: centripetal force. It's the force that's constantly pulling an object in toward the center of the curve it's on. For a turning car, that force is the friction between the tires and the road. For a satellite orbiting Earth, that force is gravity. It's all still F equals ma, but in this case, the acceleration is what's changing the object's direction. So when you put it all together, you realize F equals ma is so much more than just a little equation you memorize in physics class. It's like the operating system for motion in our entire universe. It governs a baseball flying through the air, and it governs the intricate dance of galaxies. Which brings us to one last big thought. We've seen how this law explains a crate and a car right here on Earth. But let's think bigger. What's the invisible F in F equals ma that's constantly pulling on the moon, tethering it to us, and forcing it to fall around our planet forever? Well, the answer is gravity, the same force that gives us weight, just acting on a cosmic scale.